For these examples, we are going to determine a general term for these sets here to see if these sets are infinite sets. And don't forget, the way we determine if a set is an infinite set is it has to have one-to-one correspondence. I'm just going to write it up here, 1-to-1, with the natural numbers. The natural numbers are also known as the counting numbers. So what I'm going to do is I'm just going to go ahead and I'm going to list the counting numbers here. And if you recall, or the natural numbers, if you recall 1, 2, 3, 4, 5, 6. So we now have a pattern established. I'm just going to go ahead and make this an ellipses ... This is a specific way of expressing the natural numbers. Of course, we then said that the general way of establishing or showing natural numbers is the letter N, standing for number or natural number, and showing that that pattern then continues. So we put an ellipses again right here. So that's our natural numbers. So what we're going to do is we're going to see if we can get every one of the terms or elements in this set if it has one-to-one correspondence with the natural numbers. And the way we do that is we're going to come up with a general term. I'm going to underline it right here. We're looking for a general term. And the trick is to look at the values here and determine what the pattern is. We could see a pattern has been established. 1, 7, 13, 19, 25. And if you know what the pattern is, then you should be able to determine in the ellipses here what the next 2 or 3 numbers should be. So if it's 1, 7, 13, 19, 25, then maybe the next one would be 31, and then after that would be 37. So it seems as though what's going on is that there's a factor of 6 in here. We go from 1, and then 7, and then 13. There's a factor of 6, or a difference. It looks like there's a difference of 6 each time, right? Now, we've determined that the set of even numbers has a factor of 2. So we can say that the set of even numbers, the general term for the set of even numbers, is 2n. The smallest counting number is 1. So when I put in 1, 2 times 1 is 2. If I put in 2, 2 times 2 is 4. So the same thing is going on for here. We've got this pattern, and it looks like it's 6. So I'm going to try using 6. So I'm going to go ahead and I'm going to say 6n. Now we have to write it in terms with a counting number in there. That's what establishes our general term. And the idea is since we know that the counting numbers go off infinitely, then if we wind up using the counting numbers to help express our general term for a set, that's also going to go off infinitely too. But if I take the smallest counting number, which is 1, and I slug it into here, the smallest result I could possibly get is 6. And of course, the result should be 1. So it seems like if I slug in 1, I'm coming out with 6. I need to be 5 less. So I'm going to put in -5. That's kind of similar to what we did if this was the even numbers. The odd numbers were 1 less than the even numbers, so we define the odd numbers as 2n minus 1. So if the smallest counting number was 1, then 2 times 1 is 2, minus 1 is 1. 2 times 2 is 4, minus 1 is 3. 2 times 3 is 6, minus 1 is 5, thus establishing our odd numbers. So I think this will do. So we're going to go ahead and check it. Put in my smallest number. 6 times 1 is 6, minus 5. That's 1. Put in the next counting number. 6 times 2, that's 12, minus 5. There's 7. Put in the next counting number. 6 times 3, that's 18, minus 5. That's 13. So it looks like we've got it here. Let's try a couple more. 6 times 4, that's 24, minus 5, that's 19. Put in 5, 6 times 5, that's 30, minus 5, that's 25. So I think we've got it. So the term that establishes this set and shows that it is countably infinite would be 6n minus 5. How do we know it's countably infinite? Well, because we're using the value n that represents our counting numbers, and we know that our counting numbers are infinite, so therefore this set, this general term has got to be infinite, and this general term represents this set, so this set has also got to be countably infinite. So we're going to do the same thing for this one down here. Verify that the set of numbers, and we got them here, is countably infinite set by establishing a general term for the numbers within the set. So we're going to do the same thing. We're going to see if we have one-to-one correspondence with each term or each element in this set with each element of our counting numbers. Now, it's kind of hard to establish a pattern here. It doesn't seem as though it's too evident to go from 1/2 to 3/4. Well, 1/2 to 3/4, we're adding 1/4. And from going from 3/4 to 5/6, we're putting in 1/12. So there is no pattern. But if you look at the numerators here, look at the numerators. 1, 3, 5, 7, 9. Of course, we have our ... our ellipses here. You can guess what the next one will be. 11, 13. So it looks like this is the set of odd numbers. Now look at the corresponding denominators. 2, 4, 6, 8, 10. You can guess what the next one would be. 12. So it looks like their corresponding denominators are the set of even numbers. So I guess we can say that the general term that represents this set would probably be 2n minus 1 over 2n. Again, if we slug in 1, 2 times 1 is 2 minus 1, that's 1. And 2 times 1 is 2. If we slug in 2, 2 times 2 is 4, minus 1, that's 3. And 2 times 2 is 4. We'll try one more. We'll slug in 3. 2 times 3 is 6, minus 1, that's 5. And 2 times 3 is 6. So it seems as though we've established a pattern. So since this general term, which is made up of the counting numbers can be represented by n, and we know that the counting numbers go on infinitely, and since this general term represents this set, we can say that this set also goes on infinitely.